Like I go to many conferences, and it's not matter to me like group or modulo or commutative or non-commutative or even near ring. And I always tell my colleague I'm not a religious person. And they always tell me, oh, you drink wine. Yeah, we saw that. And I don't know, but this is not what I meant. I was so happy one time I was in Germany and I was saying the same thing in one of the conferences. And one colleague, he said, wow, that's a nice way to think about it. And I felt so happy that he understood what I meant. Because, it's funny. I mean, like, I can tell you my experience in that conference in Germany. It was about a group. And somewhere in the talk, he mentioned something like, if the ring is commutative, then this is a trivial. Then I slide from my chair. You know what I mean? So, and also, we are in the commutative rings. Also, sometimes some of us become very extreme, and they say, well, if the ring is Noetherian, then it's trivial. These, I mean, I take them as jokes in a way, but I hope none of us think of that seriously. I mean, we know this is not the true. Yeah, this is my experience with conferences. Yes. Okay, this is also, yeah, thank you. First, I would like to thank the organizers, and yeah, it's good to be with the commutative ring persons here. This is also like the first speaker. Maybe this is also an old paper, but I don't remember I spoke about this except in maybe one time, maybe 5 years ago. So I want to share with you what we mean with MN closed ideal of commutative rings. Okay, this is, I have to mention with my friend and co-author David F. Anderson. Maybe some of you know him or heard of his name. The story go back to 2007. I introduced the concept of two absorbing ideal. And if you remember, two absorbing ideal, or if you ever came across this paper, it's a generalization of a prime ideal. What does it mean? Whenever you have three elements in I, A, B, C, and I, where A, B, C in R, then you have A, B in I, or A, C in I, or B, C in I. And clearly, if you want to use the term absorbing, then a prime ideal, you can call it one absorbing. Because two absorbing in the street language or unofficial language, what does it mean? Whenever you have a product of three elements in I, then you need two of them should be in I. Okay, then we generalize this concept as you expect. Me and David Anderson on N absorbing. So what N absorbing? I think all of you pick it up quickly. It means whenever you have a product of N plus one element in I, where this element in R, then there are N of the Xi's whose product is in I. So you know what four absorbing mean. Whenever you have five elements in I, then you need four of them to stay in I. Okay? And then this concept was generalized to semigroup by Darani and Buzolsky. I'm sorry if I pronounced the name wrong. These study two absorbing commutative semi-group. And then this concept, they generalize it to modulo. I mention a few names here. I cannot mention all of them. Majid Ali, Agarwal, Darani, and so on. Okay, so in this talk that rely on a paper, maybe you expect what we're gonna talk about. We're gonna talk about semi-N absorbing. What does it mean? Whenever you have x to the n plus 1 in I for x in R, then we have x to the n in I. Then clearly n absorbing will be semi-N absorbing. And semi-1 absorbing is just, semi-prime ideal. Okay? So this is like more general. So what we mean, then we went and we study MN closed ideal. What does it mean? You select randomly you fix two integers, m and n, then I to be mn closed if whenever you have x to the m in I implies x to the n in I. Okay? So for this talk, I think I would be talking about MN closed ideal. So like 5, 3. What does 5, 3 mean? Whenever you have x to the 5 in I, then x cube in I. Okay. Here are some results. That's the first one trivial, I think, just by staring. If you have a radical ideal, then it is Mn closed for all positive integers m and n. And the second one also clear. If you have an n absorbing, that is semi-n absorbing. Remember another definition of semi-n absorbing, you can say n plus 1 comma n closed ideal. So you can translate semi-n absorbing to the language of closed ideal. Okay, and this is also clear. And I think number 5 is clear. It will not take you much to prove. These are clear results. Okay, let's look at, how can I remove this? Can you see the label? How can I hide this thing here? Okay, here's an example of an ideal that is not semi-n absorbing for any positive integer n. So there are some ideals that are not n plus 1 comma n closed ideal. And I think you can, this is maybe many of you use this famous example. You take R polynomial ring, with a countable, infinite countable number of variables, and you take the ideal I to be defined this way. Then definitely this is an I, but x n plus 1, because by construction of I, this element is not in I. Okay, so the first thing, okay. Also a product. So you're gonna ask me if I have mn closed ideals for some m and n, and then I took the product. Will that be true? Definitely no. And an easy example, a product of radical ideals need not be a radical ideal. So, this is clear. And this one here, like you take some, like M1 will be correspond to N1, and MK will be correspond to NK. And you have ideals, I1 up to, and you assume that I indexed by I is MI, NI closed. So if you take the intersection, it will be closed under this restriction where M is the minimum and N is bigger or equal to the minimum. And the product is M enclosed for all positive integers where M less or equal to the minimum and N. So here are conditions when a product of Mn closed ideals will be Mn closed ideal. Number two, as you see. And of course, all of you know if the prime are co-prime, then 1 and 2 mean the same thing, right? If they are pairwise co-prime. Uh, okay, here is the question. Here is the definition. Remember that the definition of Mn closed ideal is in terms of element. So what about if we generalize this to, to give it in terms of ideals instead of element? So here is the definition. If you choose an ideal I of R, then I, we call it a strongly Mn closed ideal. So we added strongly. If you have J to the N is a subset of I, whenever you have J to the M is a subset of I. Okay? So whenever you have this, you should have this. Remember that if I remove strongly, the definition was given in term of element. Like x to the m in I means x to the n in I. Okay? That's very clear. Mn closed uh, uh, need not, here is the example. What I'm gonna say, it's clear, strongly Mn closed, definitely by definition, is Mn closed. So you're gonna ask me, what about the converse? Here is the example. We have an example where these two definitions are not the same. You can look at this, and it's not difficult. In fact, example. Uh, yeah, for the time, I cannot go to the details of the example. But anyway, in case you wonder, are these two concepts are the same? No. Of course, one of them imply the second, trivial, but Mn closed does not imply strongly Mn closed. And then we move to, like, what about if we move to ring homomorphism and localization? Then everything work out in a way nicely. Here you can look at these results. These are, usually routine or something you look at whenever you study multiplicative ideal theory. You want to know uh, what's going on when you build a group ring homomorphism. Okay, what about if we study um, rings with dimension 0? The other name, pi regular ring. And if the ring is reduced, then we call it a von Neumann regular ring. And this is that, I mean, there are many, many definitions of, or not definition, in fact. Well, you can say definition, equivalent conditions for a ring, a commutative ring, to be a von Neumann regular ring. The famous one, for every x in R, there is a y, where x square y equal x. Of course, my ring here is commutative, so because if the ring is non-commutative, then von Neumann means for every x in R, there exists a y where x, y, x equal x. But here the rings are commutative, so here is a characterization, another character, which is not very difficult, of von let R be a commutative ring, then the following statement. Yeah, this is every proper ideal of R is Mn closed ideal of R. The dimension of R is 0, and W to the N equals 0 for every W in L. Of course, as I told you, if the ring is not reduced, then we cannot use von Neumann. We call them pi-regular ring. Biregular ring also has many characterization. One of them, the dimension, the Krull dimension is 0. So here is a characterization of that in terms. And then we went to study principal ideal. I mean, here is the question. When the power of a principal prime ideal of an integral domain is Mn closed. I mean, you give me a principal ideal in R. Then we describe all the M and N, complete answer. Like if this is Mn, then I should know how M look like, and I should know how N look like. These are technical, the proof. You need to use some basic number theory to do that. And then, so this has been characterized when this ideal. And then the next thing, the same question, but we need to find the n when the power of a principal prime ideal of an integral domain is semi-in-absorbing ideal. Remember, semi-in-absorbing means n plus 1 comma n closed. How am I doing on time? Am I okay? Thank you. All right. So this is also, again, I don't think you're gonna remember these notes here, but maybe you will remember the question that if you have a principal prime ideal, then we were able to characterize the ends that make it, and we give all of them, all the ends that work. Okay. Uh, Here is why justify y powers of a principal prime ideal. And that's maybe some of you already start thinking, why are you considering only a principal? Because it will not work in general. If I try to if the ideal is not a principal, like here I have a finitely generated ideal, and I constructed an ideal, we constructed an ideal that is not 3-2 closed. So anyway, there is a reason why just principal. Okay, then okay, here is the second question you might ask me. Fix M and K. So here is K fixed here. I is a principal. What is the smallest positive integer n? So all these things, all these kind of questions are answered completely. Like you give me an ideal like p cube r. So k will be 3, and you give me m 10. So k will be 3 and m is 10. Then you ask me, can you give me the smallest positive integer n where this ideal become mn closed? Okay, yeah, we did that. Again, this is involved not fancy number theory, but in fact it does. You need some basic number theory to do that. And here is the second question you're going to ask, as usual. What about if I fix n, the smallest, here is n, and I fix k? Can I find the largest positive integer m? So k is fixed and n is fixed, and I is a principal ideal generated by this element. Can you give me the largest m? Yeah, all these kind of question, yeah, it's been answered completely, and we gave a complete description of m. Okay. Uh, and then here you define a new, you know, a new term, uh, like I is a proper ideal, and m and n are positive integer. So what do we mean with I here for the ideal I here? Is the minimum I where I is mi closed, okay? Yeah, I think. And I, of course, definitely is something less than m, because you want it mi. Of course, if I bigger than m, then no comment. There's nothing to talk about. If x to the m in I and I is bigger than m, then there's nothing to talk about. So the interesting is to find the minimum that is less than m. And we define n, and we study these things, and we have examples for many of the things. I mean, I think if you start doing that, most likely you will be doing the same thing. You, we try to answer, as many questions as we could, and I think that's a good time to stop. Here are some of the references, and maybe there are more, but these, I mean, I cannot include. And I thank you.